This is a tutorial about relational parametricity. Relational parametricity is a method for proving parametricity theorems. And those theorems is the science behind theorems for free, which is something that functional programmers may have heard of. Theorems for free is a property that purely functional code and fully parametric code satisfies certain laws, and these laws are usually naturality laws, but not always. So in this tutorial, I will explain how relational parametricity works and show how to use it to prove the parametricity theorem. First, a little bit of motivation. The parametricity theorem says that all fully parametric functions satisfy their naturality laws. So what is a naturality law? It is an equation that says in mathematical terms what it means when code works in the same way for all types. So this applies only to code that has a type parameter, or at least one type parameter. Here's an example of the function that is fully parametric. It's a head option implementation, very simple implementation for a list. If you look at the code of this function, there is nothing in the code that mentions any specific types or that works in some specific way for one type and a different way for another type. So this is what it means fully parametric. So fully parametric code, it only uses type parameters. It does not use, say, the Java reflection to determine types. And so naturality laws and other such theorems are for free in some sense, but only if the code is fully parametric. As an example of naturality law for head option, for any list and for any function f of type a to b, we have this equation, which is head option of x, and then you map with f, is equal to head option of x mapped with f. So you can map first of some list and then compute head option, or you first compute head option and then you map. The results are guaranteed to be the same. So this, for the programmer, it means that refactoring of this code is guaranteed to be correct. And that is the usefulness of naturality laws. So because parametricity theorems that guarantee naturality laws only work if the code is fully parametric, they apply only to a subset of our programming language. So we cannot use the full language with all kinds of features. We only use a certain subset, which is, in terms of computer science, a certain flavor of typed lambda calculus. Here is an example of code that does not have this property because it uses features of the language that are not fully parametric. So one example is if you take explicit matching on a type parameter with type. So in Scala you can write this code where you compute a head option in a different way. If the list has integer values, you return none. But in all other cases, you return the head option as usual. Now this certainly is an artificial example. You wouldn't want to write code like this necessarily to compute head option in this strange way. But real life code sometimes uses matching on the type. And so this works through JVM reflection, it could be useful in certain situations, but the programmers need to be aware that this is not fully parametric. This will fail, potentially, it will fail the parametricity laws if you want those laws. Another way of doing this is to use type classes. So let's suppose we define a type class like this, which will have a method returning true in all cases for all types A, unless it's an integer type. And for integer type, we will have a type class instance that returns false. And so then we can write Scala code. Well, I'm not going to write the code for this class, for this type class, but I'm just going to show how you use that. So then you have this matching, and if this type class instance gives you the true after the apply method, then you return the head option as usual, otherwise you return none. This will have the same effect as this code. And if you define bad head option like that, then you will fail naturality law. Here's an example. You take a list, you map it with some function that just converts to strings having the text x equals value, and then you take head option. So if you first do map on the list and then head option, then it's a string in the list, and then it's the usual head option. But if you first compute head option on the list, then it will be in this place in the code, and then you map and you get none. So this is an example of code that violates naturality law. So the refactoring that I showed here will not produce correct results, and that's a bug that is hard to detect. Of course, not in this very simple artificial situation, but in real life code. So what are the constructions of the language that are allowed in fully parametric code? You can write code using 9 constructions. I listed them here. So these constructions are usually taken for granted in functional languages. All functional languages support them. Scala, Haskell, OCaml, F#, Swift, Rust, Elm, and so on. They all support these constructions. So you can use unit value in any place, and not only unit value in the usual standard way, the unit value, empty tuple, but also equivalent values, fixed values of some type that is equivalent to unit in some way. Fixed values of fixed types you can use like this. You can use the bound variable. So if you have a function with an argument, you can use that argument. Now this sounds trivial. Of course, you can use the argument of the function if it's given, but that is important, that the code is allowed to use that. You have to list what is that you're allowed to use, because otherwise you cannot prove properties of that code. You have to show exactly what it means that the code is fully parametric. This is not some kind of heuristic approximate idea, fully parametric. It's code that is written only using specific constructions. And so you are allowed to do this. You're allowed to use arguments of a function. You can create a new function, writing code like this. You can use a function that you already have, writing code like this. You can create a product value given some a and b. You can create a tuple, which is a product type. If you have a product type value p, you can use it to extract values out of it. You can extract the first one or the second one, or other ones. And in case classes, you can extract by name. Or you can do this via pattern matching, but it's just different syntax for the construction number 6, which is to use a product type. You can create a value of a coproduct type like this, for example. and you can use it by pattern matching, for example. You can use a recursive call. So if you are trying to define a function function f map, like in this example, then you're allowed to use that function to call it while you are defining that function. So you're allowed to use that function inside of its own code. That is a recursive call. And this is an example of a small program that is written using these code constructions. So this is a fmap method for a list of pairs. And the type signature is standard. You take a function from A to B, you return a function from list AA to list BB. And I annotated here the constructions that are being used in each place of the code. So for example, when you write in Scala this syntax, the curly braces with case, that means you're creating a function. So that's construction number 3. And then the case itself is the pattern matching that uses a coproduct value, which is the list. So the list is a recursive data type defined using a coproduct. It's nil or head and tail. So then you pattern match on this. This is construction number 8 to pattern match on a coproduct type. Then here you use construction number 1, for example, to use a fixed value of a type. Here you use construction number 6, which is using a coproduct type, using a product type, because the list contains a product of head and tail. It's just a different syntax for product. And so on. So here you use the bound variable. This variable f is bound. It is given to you as an argument, so you are allowed to use it. Here you're using a function. So you're applying this to argument. Here you're taking the first element of a tuple, so that's construction 6, and so on. So here's, for example, construction 5, you're creating a new tuple. And here's the construction 9, you're using recursive call. So this code uses each of the 9 allowed constructions. So this is just an example to illustrate what it means to write fully parametric code. So this is 9 constructions that are allowed. So let's go back now to relational parametricity. It's, like I said, a method for proving parametricity theorems. So the main references for this are the papers by Reynolds and Wadler. The Reynolds and Wadler papers, so the links are in the slides. They're very well known. That first explained relational parametricity and gave its use. Now, these papers are pretty old now. They read a little outdated, and also they're hard to understand. I never understood the first paper of these, the Reynolds, and I have a very hard time understanding the second one. So from the second one, I understand some part. And there are very few good pedagogical tutorials on the methods in these papers. So jumping. There are 2 tutorials that I could find that explain relational parametricity. One is a paper on a relation of functions, and the other is Algebra of Programming, the book that you can find. Now, my tutorial, which is this one, does not follow any of these papers and books. I found a different way of explaining relational parametricity that I think is easier to understand. It derives equivalent results, but it's just a little more modern and easier to follow. There are alternative approaches to parametricity, which is the so-called dinaturality. So there are some papers I link here in the slides. Dinaturality is a generalization of naturality for functions that are not covariant in their type parameters. But actually, dinaturality law is weaker than relational parametricity. It is a consequence of relational parametricity, and in some cases it's sufficient. So quite in a few cases where you don't need full relational parametricity, you just need to write dinaturality law, and that's much easier. I already recorded some tutorials about this. It's a lot easier to write down the dinaturality law, and in most cases that will be sufficient. However, there are some proofs. I can indicate two of them. One is Church encoding of recursive types. So that requires type signatures of this kind for all A, and then some f of A function to A to A. Now this type signature is too complicated for dinaturality to work. So dinaturality does not give enough of information about this function to prove the properties that you need about it. And second is fold. So the fold signature, you could think, no, let's write a fold like this. You have a function a to b to b. You have an init value of type b, and you get a b. This type signature also is too complicated for dinaturality to work. With respect to the type parameter b, is a b in a covariant position, contravariant position under the function arrow, and again here, just like here, is too many positions in which the same type parameter occurs, and this is an indication heuristically that dinaturality is not going to be sufficient. So you need to have full relational parametricity for these proofs to work. So just to explain that these are proofs of theoretical properties of these functions. So programmers do not need to study these proofs in order to be able to use the Church encoding or the fold function or its properties. They need to know these properties. They do not need to have mastered the proof techniques. But of course, at some point you might want to ask, what is the proof? Is that really true? And that's what you will have to do then. So let me then go on to naturality laws in order to motivate why we need parametricity and what we get out of it. So I showed an example of head option. Naturality law of head option was that you apply map after head option, and it's the same as you apply map before head option. This is generalized to a function t that goes from f of a to g of a. So instead of going from list of a to option of a, and instead of list you just have some f, and instead of option some g. So that gives you a more general situation where you can apply a map of some function f before applying t, or you can apply a map after applying t. So that should give the same result. And this is a diagram that shows that you first take some value of type f of a, you apply the t, with type parameter a, you get g of a, and then you do a map of f, and you get g of b, where f is some arbitrary function a to b. Or you can first take a value of type f of a, apply map to get f of b, and then apply the transformation t with type parameter b to get a g of b. And the naturality law says that if you do this or if you do that, the results must always be the same for all functions f and for all types a and b. So this is a naturality law in a general form. The name naturality law comes from category theory, where these are natural transformations between some functors. But this is just the reason why we're calling it like this. We don't need any category theory in this tutorial. So the proof of naturality law we would like to understand. We need to take the code of this natural transformation and take it apart and perform induction in the proof. So we can do this because the code is guaranteed to be made up of 9 code constructions. And so, for example, this code of head option is made of these 9 code constructions as well. So we can take it apart, and each one of these parts will again be purely functional and fully parametric code. Just as an aside, the bad examples here, they're still purely functional. There are no side effects here. There are no mutation. But this is not fully parametric. So this is a stronger constraint than purely functional. So we would have to decompose the code of t into its sub-expressions in order to prove that it satisfies the law. And the sub-expressions need also to satisfy the same law. But this is not possible, because sub-expressions will be of types not necessarily of this shape, and they may not be covariant in A. And so there might be sub-expressions that are complicated, that by themselves do not have this type signature, or they're not covariant in A. But as a result of the code, everything has this type signature, and so on. So it is not possible to directly prove naturality law in this form by induction on the code of t. And if the sub-expression does not have this shape and it has non-covariant type constructors, then we cannot lift the function f. So we know that if the function f is a to b and the type constructor f is covariant, we can lift it to f of a to f of b. But this cannot work if f is not covariant. So for contravariant, we can lift b to a like this. But in general, there will be some sub-expressions. Let's look at the code again. Some sub-expressions like these, or like these, where it's neither covariant nor contravariant. So there are some a type values of type A as arguments of function, values of type A as results. In general, the type constructor will neither be covariant nor contravariant in its type parameter. Another example of this is that fold left, which you can write like this. With respect to the type parameter A, it is neither covariant nor contravariant. It is not of this form. Also with some covariant f and g, you cannot write it in that form. So it's too complicated, because some occurrences of the type constructor are in covariant position, like this one or this one. Other occurrences are in contravariant position, like these two. and it's just all mixed up. It's too complicated. So it's not possible to write this type signature in the form of some covariant f of a being mapped into some covariant g of a. So that is a difficulty. And if we have to prove laws for this kind of function, then we cannot even formulate that law, because we cannot lift arbitrary function f to the type constructor that is not covariant and not contravariant. So that is a difficulty. We cannot even formulate the law. So we need to first formulate the law in a different way so that it can apply to arbitrary type constructors, not necessarily to ones that are purely covariant and purely contravariant. So that's the next step. To solve this difficulty, first of all, we replace functions f from a to b by relations between types a and b. So instead of saying that b equals f of a, we say that the values a and b are in the relation R. So this will be the syntax for this presentation. I will explain in more detail what it means that we have a relation between types. The next step will be that we will find out that we can lift relations to arbitrary type constructors. So that is the reason why relations solve the difficulty. It's because relations can be lifted to an arbitrary, not necessarily covariant type constructor using a function that I call RMap. So it's like fmap, except for relations. Finally, we need to reformulate the naturality law in terms of relations. And instead of the naturality law that we had here, where for an arbitrary function f we have this diagram, we will have a naturality law like this, where for an arbitrary relation R, we will have a similar diagram, where the f of a is related to f of b by the lifted relation. G of a is related to g of b by the lifted relation. And f of a is mapped to g of a, f of b to g of b, using this function. So to read this diagram, we need to start with two arbitrary values on the left. So one value of type f of a, one value of type f of b. And then we have also an arbitrary relation between types a and b. These must be in the relation lifted to f, and then we require that the results of applying the transformation must be in the relation lifted to g. So that will be the plan of how relations solve the difficulty with proving the naturality law. But the price is that we're not going to prove naturality law anymore. We're going to prove a relational naturality law, which is formulated using relations, no longer with functions. So that is another thing that I will touch on, and I'll explain how that works. So let's look at relations now. What is a relation? In the terminology of relational databases, a relation is just a table with two columns. The columns are of types A and B, so they have values of types A and B, respectively. And one row of the table, you can imagine, has one value of type A and one value of type B. So having this row means that the value A and the value B are in the relation R. So they are in the table, and the table is a relation. And so the values A and B are in the relation R. So R is the name of this table. That's how relations are interpreted in terms of relational databases. So we'll have a number of rows showing which values A and B are in the relation. So mathematically speaking, this means we have a subset of the product of A and B. So all possible pairs AB are this set, the Cartesian product of A and B. They're all possible pairs, but we do not allow all possible pairs in this relation. We only show which ones are allowed. So we show a subset of this set, and that is a relation. So a relation is a subset of the Cartesian product. And then if the pair AB is in that subset, we write that A and B are in the relation R. So that is a definition of what it means to have a relation. So it's some subset of A to B. How we define that subset, that's another question. So we can define it in different ways. In general, the relations can be many to many. Note that functions A to B are many to one. So many values of type A might be mapped to one value of type B, but not vice versa. So if you have a function of type A to B, you can also view it as a relation, which I will denote rel of f of type A to B. So this notation I just invented here. It means the type of the relation. So relation R has this type. It means that it is a relation between types A and B. So a function f is transformed into a relation rel of f, and we define that by saying A and B are in rel of f if B equals f of A. So a function defines a relation. So this is one way of defining a relation. Not necessarily the most general, of course. If we take an identity function between A and A, that defines an identity relation, which we denote by id. So this relation is very simple. X and Y are in identity relation only when X is equal to Y. So it's only equal values that are in the identity relation, because then, you know, this is a B equals f of A and f is identity. So B equals A. So that is the identity relation. And here's a relation that can be many to many, which we can define using two functions. So suppose I have a function f from A to C and a function g from B to C. So then I define a relation I call pullback fg. Doesn't matter why it's called pullback, it's just a mathematical term. And this is a relation between A and B, which is defined by this requirement. A, B are in that relation, in this pullback of G, which is R here. It means that f of A equals G of B. So you can apply f to A, you can apply G to B. The results are values of type C, and they must be equal. So because functions f and g are arbitrary, for any f and g we can have this pullback relation. Some functions f and g will define a many-to-many pullback relation, no longer one-to-many or many-to-one. So this pullback relation in general will not be equivalent either to a function of type A to B or to a function of type B to A. So there are other ways of defining relations using relation combinators. So if you have already some relations, then you can combine them and make new relations out of them. So here are the relation combinators. For any relation R, we have an inverse relation, which is B to A. Well, this is kind of trivial. We just change the order of A and B. AB is in R when, so AB in R is the same as BA is in inverse of R. So it's then easy to see that the inverse operation is its own inverse. So this operation does not lose any information. So any relation A to B, you can invert it. It contains exactly the same information as the initial relation. I would like to distinguish, though, this relation and that relation, although they're very, very similar and pretty much the same, isomorphic to each other, but I would like to distinguish them for clarity. So then A and B are ordered. So A and B B and A. It's confusing if you don't order them. But this operation shows that they are equivalent. So in some sense, relations are not really ordered. So they're between A and B, but they're not in the direction from A to B or from B to A. They're completely unordered. Now, if I have two relations A to B of type A to B, R and S, then I can take the union or intersection of these relations. Now, this is kind of easy because relations are subsets. Right, so relation R is a subset of the product A and B, and relation S is also a subset of A and B, and so we can have a union and intersection of these subsets, and it's again going to be a subset of A and B. So these are the definitions of what those mean. Finally, important operation is composition of relations. If you have a relation between A and B and a relation between B to C, then we can define R compose S, and that is going to be a relation between A and C. So this corresponds to join in relational databases. You have a table with columns A and B, you have another table with columns B and C, you join them on the column B. Now the join works by taking values in the column B that are equal. And so we define the composition in the same way. So A and C are in this new relation U. When there exists a value B, which is both in the first relation with A and in the second relation with C. So this is a definition of the composition. It satisfies a law, which is that if you want to compose R with S, you can also compose S with R if you invert these orders, and you invert them with inv. So this law is kind of clear and obvious because we just invert these, and the definition maps to the other definition. So this law explains that composition is really not directional. So it's not R and then S, or S and then R. It's really not directional. Relations are not directional. They're not from A to B or from B to A. They are a relation between A and B, but not in the direction between them. And so composition is also not directional. R and S can be composed if they have a common type here. And it doesn't matter if you consider first R or first S in that composition. It doesn't really change anything. So this is this law. Also, the composition has associativity and identity laws with respect to the identity relation. This is a very important property of the composition. Finally, it preserves the composition of functions. So if you have function A to B and function B to C, you can take a composition of these functions, f and then g, and the relation corresponding to that function is going to be equal to the relation of the relational composition between the relation of f and the relation of g. So that is an interesting property. Finally, the pullback relation can be defined using a composition operation like this. The pullback is just, you have a relation of f, and you compose it with the relation of g turned inverse. Here are some diagrams to show how that works. I want to prove that the pullback of fg is the same relation as this. So I take some a and b, and I want to prove that this condition, ab in pullback fg, is equivalent to ab in this. So if I prove that these are equivalent, I will have proved that pullback is equivalent to that composition. So how do I prove this? So here's the diagram. I have this relation between A and C, which is the F viewed as a relation. And then I have relation between C and B, or B and C, if you wish, by inverting the G relation. And I take the composition of these. And the composition is a join on C. So C must be equal in the first relation and in the second relation, which means that f of A must be equal to G of B. And that is a relation that we want to prove. So there exists some C such that AC is a relation of F and CB is an inverse relation G. But if you write down what that means, it's not Z here, it's C. So C is such that C is equal to f of A, because this must hold. And C is such that C is equal to G of B, because this must hold. But C exists because we can always compute f of A. A is given, F is given, G is given. So we can always compute f of A. And so C will exist, and so it will be equal to G of B, because this is the condition of the first relation. So in this way you show that that from here follows this, and similarly backwards. So then the second condition is equivalent to the first condition, and so I have proved this last statement. I will not prove every other law here, but it can be done in a similar way. It's not very difficult. So finally, we have understood what relations are, but what do we do with them? We need to lift relations to a type constructor. So this is a central place in understanding of parametricity, relational parametricity, is that relations can be lifted to an arbitrary type constructor. And the result will be a relation between f of A and f of B. If you had a relation between A and B. How does this work? Because the code needs to be fully parametric, the type of that code will be not arbitrary type, but it will be made of specific types and type constructions. So for example, if you take a look at the 9 code constructions listed here, and you try to see what types they produce, what kind of types you can get if you write code using these constructions, then you find that there are only 7 possible type constructions that you can get out of this code. And these are the unit or another fixed type, identity functor, so you can get this, product, so if you have some G and H, then you can take a pair or product, a coproduct, if you have G and H, you can construct an either GH, a function type, so you can construct a function, a recursive type, so if you have some type constructor with 2 type parameters, then you can recursively define a type constructor F like this, and you can implement values of this type. And finally, universally quantified, because your functions are allowed to have type parameters. Then you can have another type parameter, say z, and then you have a function with a type parameter z, which returns type g of az, where a is another type parameter, and the result of this only has one type parameter, a. So you're allowed to write code like this. I did not show examples of this code, but you can do that. So now, how do we define the lifting of an arbitrary relation to an arbitrary type constructor? Well, obviously not to an arbitrary type constructor, but to a type constructor that is defined using one of these 7 cases. And in each of these cases, we need to define RMAP. So similarly to how a functor defines fmap, it's very similar to what is allowed to define fmap. If you look at how fmap would be defined for each of these cases, then you just kind of get inspired to define RMAP. And that's something a programmer can easily do, how to define fmap. It's just a function with certain type signature for each of these constructions. And that will give you an idea of how to define RMAP, which I'll show on the next slide, but I'm just indicating how you can come up with this. And then you will prove by induction that you have constructed this relation. The inductive assumption is that for these G and H here, you already know how to construct the lifting. So you already know how to lift arbitrary relations R to G and to H. And if you already know that, then you show how to lift to F. So that is going to be the proof by induction. There are some details I'm going to talk about for this proof. For the G of AZ, you have in 2 places you have G with 2 type parameters. So you need 2 liftings. You need to lift relations with respect to the first type parameter, and also you need to lift with respect to the second type parameter separately. So this also needs to be defined, obviously, in the same way. So we assume by induction that this is already defined. However, we need to know the certain property that these liftings commute. So if you lift a relation with respect to the first type parameter and then another relation with respect to the second, you can do this in any order. That is important for correctness. So that is something that one has to prove also, that the commutativity law for liftings, if you have 2 type parameters. And also, if you have a composition of functors, then you expect a composition of liftings, just like fmap. So you first lift a relation between A and B to a relation between H of A and H and B, and then you lift the G. So here are some diagrams to clarify. Let me first clarify this. So you lift a given relation R with respect to H, you get a relation between H of A and H of B, and then you lift that relation with respect to G, and then you get a relation between G of H of A and G of H of B. So that's how you define lifting if you have a composition. This is a diagram that illustrates the commutativity theorem for liftings. Now, this is a theorem that needs to be proved together with defining the lifting, because it uses the same induction on the structure of G. Here is the diagram that illustrates how that works. Suppose you have a type constructor G of AX, and you have 2 relations between A and B and between X and Y. Then you lift this between A and B with respect to the first type parameter. You get a relation between G of AX and G of BX. You lift here G of AY, G of BY, the same thing. And also you can lift the S relation with respect to the second type parameter of G, and that will give you a relation between GAX, GAY, and also a relation between GBX, GBY. And finally, you perform composition of these relations, because you can compose GAX, GAY, GAY, GBY. So they have a common type, which is GAY. You can compose them, and you get a relation between GAX and GBY. Or you can compose these 2. So the commutativity theorem says that the two compositions always give the same relation between GAX and GBY. The simultaneous lifting of R and S with respect to A and X at the same time to BY. So this is well defined. You can do it in any order and the result is the same relation. You have to prove this, and you prove this in the same way by induction. So I will show you the definitions. I will not show all the proofs of this, but I'll show you the definitions of how we lift a relation R to a relation R map of R in the 7 inductive cases. When you have a fixed type, then the R map is just the identity relation, because f of A and f of B are both T. So you have a relation between T and T, and so you just define that to be the identity relation. If you have the identity functor, then R map of R is just R, because what you need is to define a relation between f of A and f of B, and that's just the same as A and B. So relation R is unchanged. If you have a product, you need to define when this and this is in R map of R. So G1 is of type G of A, H1 is of type H of A, G2 is of type G of B, and H2 is of type H of B. So let me just write it down, what types these are for clarity. So if I show when this is true, when these two are in a relation, that's the same as I define this relation. So they are in this relation when G1, G2 are in this relation, they lift with respect to G, and H1, H2 are in that relation, lift with respect to H. By inductive assumption, I already know how to lift with respect to G and with respect to H. When f of A is either G of A, H of A, then I need to define a relation in a similar way. I define that either the left and the left are in the relation, or the right and the right are in the relation. But so types here are the same. This is G of A, and this is G of B. So I define this relation lifting to either such that I never have a relation between left and right. So always left with left, right with right, but never mixed. And the relation left with left holds also only when G1 and G2 are in the lifted relation with respect to G, and similarly for H. Now for the function, I define the relation between two functions. Now these are of type G of A to H of A, and this is of type G of B to H of B. So these two functions are in the relation when, for any arguments that are in the relation, the results are in the relation. So the first is say, for any arguments for these two functions that are in the lifted relation with respect to G, the results of applying the two functions to the two arguments must be in the lifted relation with respect to H. Now this is designed to reproduce me this situation where you have a function and I say when the two arguments are in the lifted relation here, then the two results must be in the lifted relation there. So that is why it is defined like this, so that I have correct naturality laws later. For recursive types, I define our map of R, which is first I lift with respect to A, and then I compose it with lifting with respect to the second type parameter, and then I use the same relation R map recursively. So recursively, I already know how to lift f of A to f of B, to relation f of A to n f of B. So I lift that relation in here, and I lift the same relation in here to obtain a relation between g of A f A and g of B of B. So that is how I have to do it. And finally, for the universally quantified type, this is a much more interesting construction. I define in the following way. Since I have an extra type parameter, I need to specify here another arbitrary relation S between any types Z1 and Z2 here. So this lifting of R is given between A and B. I need to lift it to this. It introduces a second arbitrary relation into the definition. So then F1, F2 is in the lifted relation when, for any other relation S, the results of applying these functions to their type parameters are in the relation, which is here the relation R is lifted to get A to B, and here the relation S is used to lift Z1 to Z2. So then you get the relation between G of A Z1 and G of B Z2. And that should be the composition of the two liftings. So this is a mouthful, but this definition is enough to define the lifting for any type parameter, for any type constructor. Let me show some examples. So there are two main examples of relations that are generated by functions. So the usual one, the rel of f, which is just a graph of the function, and the pullback. And let us now lift rel of f and lift pullback, if we can, to the following examples. To constructor f of A that is covariant, g of A which is A to A, and h of A which is A to A to A. So if f of A is covariant, then it turns out that lifting a functional relation is the same as the lifting of the function to that type constructor. So f map of f is a function of type f of A to f of B, and so the rel of this is a relation between f of A and f of B. And the same is for the pullback. It's very interesting, but it can be proved quite quickly, because the pullback is a composition, and lifting is compatible with composition. So lifting of composition is composition of lifting. That's another theorem that you can prove for the functor, for covariant type constructors. And then, so the result of this example is that for covariant type constructors, lifting of relations is completely compatible with the lifting of functions in the usual way to covariant type constructors. Now, more interesting examples that are not covariant. So this is a type constructor. What does it mean that two functions here are in this relation? it means that when any two values a and b are in this relation, then the results of applying the function to this argument are in that relation. So fa and fb needs to be applied, each of them to a and to b. So fa is of type a to a, fb is of type b to b. So when is a function of type a to a in a relation with a function of type b to b? When this holds. And we can rewrite that as an equation. So fa must commute with f and fb. So fa and then f must be equal to f and then fb. So this is a relation in the form of a pullback, because it's an equation. It's some kind of function of fa, some kind of phi of fa equals some kind of psi of fb. So that is a pullback relation. So that's an interesting thing, that if you have a functional relation and you lift it to a non-covariant type constructor, you get a pullback relation, which is not a function anymore. If you try to lift a pullback, it's much more complicated. Then you cannot really write it very easily. No longer a pullback. So lifting to a covariant type constructor preserves the structure. You lift a functional relation, you still get a functional relation. You lift a pullback, you still get a pullback. But lifting to a non-covariant type constructor makes things more complicated. And finally, this example is even more complicated. So if you write it out, then first of all, there must be this. So for any two functions, a to a and b to b, in a relation, which is lifted in the previous example, the results of applying these functions must be in a relation. So if you write it out, you have this condition. And this is not a pullback relation. So you cannot express p through q in this relation in order to replace this condition with a single equation. So the conclusion here is that with this type constructor, lifting even a simple functional relation to that type constructor produces a relation that is not in a pullback form. It is a complicated relation with arbitrary arguments of type, functional type, and they must satisfy some complicated condition, and only for those there must be some other complicated condition. It is not easy to use that kind of relation. It is not easy to take it and draw some conclusions from it in the form of an equation. You have to find specific p and q that satisfy this, and then you will have an equation. But that's only for specific p and q. So you could draw conclusions from it which will be weaker than this full relational law. But you will be able to use those conclusions maybe more easily. So it's hard to use relations that do not have a form of an equation, simple equation. They have this form for some arbitrary p and q that satisfy this condition, and some other condition must be satisfied. That's hard to use. But these are the examples that illustrate how lifting of relations work. So for simple cases, lifting is simple, but it rapidly becomes complicated when you have type constructors that have this kind of structure, where you have type parameter in all kinds of covariant and non-covariant positions under the function. That is typically when usage becomes complicated. So now we are ready to formulate the relational parametricity theorem. So we previously considered these functions of this type signature, but actually we can simplify, and we have to simplify in two steps. So first, we notice that this has a function type, and function type is one of the constructions. So instead of saying that we prove a specific law, like for example this relational parametricity law, we just say, well, let's call this type P of A. Let's just put this all inside the big P of A. It doesn't matter since we don't require P of A to be covariant in A. So because of the definition of the relational lifting for function types, the result will be a simplifying formulation. So any fully parametric function t of type P of A for any relation R satisfies this relation. So T of A and T of B are related by this lifted relation, which is of type P of A related to P of B. So this is simpler than saying, oh, first we need to have some values here of type f of A, f of B, they have to be in this relation, and then we require that. So that is equivalent, but we will have to deal with this as one of the induction cases. So our formulation will become just like this. Finally, we can also use this type parameter. This is one of the constructions that we had. This is this instruction. And we just say, well, TT with no type, P with no type parameters, the TT is in the lifted identity relation. Now this is actually the formulation that you can find in the Wadler paper and in some other papers. That any fully parametric closed with no type parameters expression T is in a relation with itself, but they don't say what that is. They don't spell out what that relation is. They make it complicated. So in this formulation, this becomes much clearer. We have a specific relation, which is identity, identity between fixed types. There are no type parameters, and we just lift that to the type constructor P, which already will contain an arbitrary type parameter inside and so on. However, this formulation is not convenient for proof. So for proof, I will use a different formulation, which is more convenient. And this formulation is not convenient because sub-expressions of T will have free variables. And we need to have a parametricity theorem for expressions containing free variables. For example, this function will have an argument, and this will be an expression containing that argument as a free variable. But we need an inductive assumption for this sub-expression, which will be inconvenient to have if we don't formulate the parametricity for such expressions with free variables. So that's why we go to a formulation, which I'm going to show here. Any fully parametric expression with a type parameter, it's much more convenient to have a type parameter, not to hide it and to talk about this strange thing that term is related to itself. This is very confusing. Much easier to say, well, we have a term with a type parameter, and then we have this relation between T of A and T of B, which is the relation lifted to a type constructor P from an arbitrary relation R. So that is what we're going to do here, but we're adding a free variable. So let's Z is a free variable. In other words, it's some kind of argument which is not defined inside T of A. So for example, T of A of Z, it could be, let's say, a function x going to, let's say, x of Z. Right? Now, the type of x needs to be correct for this to work, but we can easily do that. but z is not defined inside this code. Z is a value defined outside somewhere before we can use this code. So that's what it means that z is a free variable. It's a value that's defined in an outside scope somewhere, where in that scope we can use this expression because z is defined there. But right here, z is not defined, so it's a free variable. So that's for those expressions that we want to formulate the parametricity property. So for any free variable of some type q of a, so the type of free variable could also depend on this type parameter a. So for any of these, for any relation between a and b, and for any two values of this free variable, which are of types q of a and q of b, and they are related by this lifted relation, then the results of this expression applied to these free variables must be in the relation here. So this is a little more complicated. This is exactly the same as the formulation for the function construction, except there's no function. T is not a function. T is an expression that uses z as a free variable, so like this. So this is not a function of sort z going to something. So there is no z argument explicitly in here. So that's why we need this formulation, because some sub-expressions of t will have this form with free variables. What about more than one free variable? Well, that's not a problem. We can just put them together into a single tuple. And this tuple will be of some type, and this is general enough to have just one free variable of some arbitrary type, and the tuple will have some type as well, so we just don't need to talk about more than one free variable in the formulation of this theorem. So we're going to prove this theorem. This is the parametricity theorem that will be in focus. How will we use that theorem once we prove it? So here's an example. Let's say we have this code. Oh, this is a mistake. This must be lowercase a. So this is a code of the identity function of type a to a. Let's apply parametricity theorem to this code. For any types a and b, for any relation R between a and b, t of a, t of b must be in the relation lifted to R. Now this lifted relation has this type, the relation between functions a to a and functions b to b. So what does it mean that some p and q are in that relation? It means for any arguments a and b, if a and b are in R, then p of a, q of b are also in R. And so it means, you can translate that back, this relation between t of a and t of b, it means for any values a and b, if a and b is in R, then t of a, t of b are in R. So that will be the result of parametricity theorem. How do we use that in practice? It's easy to use that in this case. We just say we choose the relation R to be a relation obtained from a function. And we use this relation obtained from an arbitrary function between types a and b. So then the relation means f of a equals b. And the parametricity law means if f of a equals b, then f of t of a equals t of b. And equivalently, it's like this. So for any a, f commutes with t. So t is a function of this type, and it commutes with any function a to b. That is the result of applying the parametricity theorem to code of this type. So the parametricity theorem says any code which is fully parametric with this type signature will satisfy this relational law, and then we just specify that law for a relation which is obtained from a function, and we get a function as a result of the law, and that is easy to use. And then we can prove that t must be an identity function. So any function with this type signature must be an identity function because it must commute with any function f. Let's choose the function f like this, which is a constant function returning a fixed value b of type b, and then we say f of t of a equals b because it always returns b, and it must be equal to t of f of a, which is t of b because f of a always returns b. And so b equals t of b for any b. So t is the identity function. So this is the result of applying parametricity theorem to this case. How do we prove this theorem? Now, the theorem says that this expression of this type, of this shape, must satisfy the relational parametricity law. We need to take a look at the structure of this code. Now the code must be given to us, right? We prove that any expression of the type signature that we can get satisfies the law. So the structure of the code must be made out of the 9 code constructions that we listed. That is what it means to have purely parametric, fully parametric code. So we write a proof that decomposes this code into the 9 constructions, and for each construction we will have some sub-expressions. The sub-expressions will be of the same shape. There will be some kind of expressions parameterized by a type parameter with some free variables. It's always going to be like this, because if you look at the 9 code constructions, there's nothing else that you can have. You have expressions that have some functions, or you can have this, for example, or you can apply a function, but it will always be some expressions with some free variables. So because this could have some free variables, then this will have some free variables. F itself is an expression of the same kind that can have free variables, and so on. So whatever you do, you are always going to be within the same class, of expressions of this kind. And so, because this expression of this kind is decomposed into sub-expressions of the same kind, we can use induction in this proof. So that is how the proof works. But of course, each time it will be a different type, because the relational parametricity law depends on the type. So T of A of Z is type P of A, and Z is type Q of A. When we decompose this T into sub-expressions, then we'll have perhaps different types P and Q for each sub-expression. But that's fine, because then it's still the same class of sub-expressions, the same class of expressions, and we can use inductive assumption. So the bound variable Z itself also will have to satisfy the same law, because ultimately it's going to be of the same kind, expression of the same kind. And so that's how the proof will be organized. So I'll just outline of how we prove the first 4 constructions. Now all the proof, it goes in a similar way. So here's, for example, constant type. So the code of the expression t is just constant C, it's fixed value of a fixed type C. Then by definition of lifting, now the code of lifting is just identity. So identity relation, because it's a fixed type, does not depend on A. So when we lift a relation between A and B to the type of this, then we get identity relation between C and C. So then it's just the identity relation, and it holds because this is just a constant, so C and C is always in identity relation. And so then this is consistent. Second construction is to use the bound argument. When we use the bound argument, that means the code is just Z. So this is this bound argument. It's a free variable which we defined outside of the scope of this, and so we just use that free variable. What we need to prove is that if there are two values z1 and z2 of the type Q, and they are in the relation Q, then T of z1, T of z2 are in the relation P, or map P, lifted to P. But this is exactly the inductive assumption. If z1, z2 are in this relation, then T of z1 is exactly z. Sorry, it's not an inductive assumption. This is a trivial statement. This is always true because T of z1 is equal to z1. T of z2 is equal to z2. And P is actually equal to Q. So this is the same. R map of Q and R map of Q of P are the same. And so z1, z2 are in R map of Q, then z1, z2 are in R map of Q. It's a trivial logical statement. So this is true. This third construction is to create a function. So the code of T is of this sort. Now, H is a new argument. So we're creating a new function. I could write maybe like this in Scala to be more explicit, that we're creating a new function. And S is some expression which has type capital S. It's a new type, different from P. So this entire thing has the type P of A. So P of A is a function type, which is H of A to S of A. So that's generally what we can have. And what we need to prove is that when there are two values z1 and z2, and h1 and h2 are these two arguments in a relation lifted to h, then s of z1, h1, s of z2, h2 are in this relation. So we need to prove that. But this is exactly what we have for inductive assumption for S. Now, S of ZH is a sub-expression which, by assumption, satisfies the law. Now, the law for this sub-expression will be formulated first by putting Z and H into a single tuple as a free variable. And then that free variable needs to be in a relation, but we know how to define relations for tuples. It's just first elements of the tuple are in the first relation and second elements of the tuple are in the second relation. And so we find that what we need to prove is precisely the inductive assumption for S, which holds by assumption. And the fourth construction is to use the function. So we have the code, which is applying some function g to some argument h. And both g and h could be expressions that depend on z, on this free variable z. So g would have some type like this, and h would have some type like this. And inductive assumption needs to be used for G separately and for H separately. So these are the two inductive assumptions for G and for H. And what we need is the law for T, which is if Z is in this relation, then G of H is in that relation. And so this is just a logical a syllogism from these two. So if this is true, then this is true. If this is true, then that is true. So we just substitute that is instead of H1, that instead of H2, and we get the condition for this, so we obtain that. So in a similar way, we prove all of the inductive cases. There are quite a few technical difficulties maybe in this proof that needs to be done more carefully. Need to use commutativity law for composition, need to use some other laws, but this is basically how the proof goes. So I'm not going to go through the proof fully. The first four are enough. I'm just going to conclude now that relational parametricity is a powerful technique that allows us to go around the difficulty that we cannot lift functions to type constructors that are not covariant, but we do lift relations to type constructors that are not covariant. So we can lift, and in this way formulate a law for any function of any type signature. Now the price for that is not only that we have to write code in a fully parametric way, but also that we get a relational law as a result, not an equation. So we still have to get an equation out of it. So I showed an example how we can get an equation out of relational law, but it's not an easy procedure. So there are cases where it is not possible to get an equation that is equivalent to the relational law. The relational parametricity law in some cases is more powerful than any equation that you can have for that function. But in many cases, you just have an equation. So this technique has been generalized to many different settings, to all kinds of different languages, because this, as I showed, this technique only works as long as you restrict your programming language to a specific set of code constructions. But you can have more code constructions than what I showed. Certainly for different programming languages, more complicated code constructions could be allowed. So for instance, you can have languages with gradual typing, with higher candidate types, with dependent types. And for all of these different languages, you need to formulate how to lift relations to type constructors of different kinds, and then you have to prove that the relational law holds for code that is written using these new features that you added to the language. So I showed you kind of a baseline. So the baseline of all functional languages is these 9 code constructions. But there are certainly the same techniques have been generalized to different programming languages. Now, I would like to emphasize that this is not an easy theory to learn or to use. You cannot write code that manipulates relations. Relations are manipulated symbolically. You write proofs about them, but you cannot write easily code that computes with them. So either you do it by hand, symbolically, or on paper, or with proof assistance, which is an advanced technique, certainly. So it's not easy to get results out of relational parametricity. You need to develop the techniques and experience working with this kind of symbolic calculation. Even if you learn these techniques and derive a relation for your code, then you get a relational law, and it's difficult to interpret that law as equation for your function or law for your function. And so that is another step that needs to be done. In a different tutorial, I showed how you can write, in many cases, directly just the equation, the law, without going through relations, and that's what I would recommend. But there are some places that I showed that do require the full power of relational naturality law. One of them is the Church encoding of recursive types, and the other is the fold function. So more details and full derivations and proofs I'm writing up in the book that is fully on GitHub. It's a full text of it is on GitHub. So I invite you to take a look at it and let me know what you think. That concludes the tutorial.